Hello, and welcome. Today we're diving into the essential topic of accuracy in mathematics. In many real-world situations, exact numbers aren't practical or even necessary. Instead, we use approximations. By the end of this lesson, you will be able to round numbers to a given degree of accuracy, use significant figures correctly, estimate answers to complex calculations, and determine the upper and lower bounds of a measurement. These skills are fundamental for making sense of numbers and calculations in science, engineering, and everyday life. Let's begin with the most common form of approximation, rounding. Rounding allows us to simplify a number to make it easier to work with while keeping its value close to the original. Imagine a gymnastics competition with exactly 28,617 attendees. Reporting this exact number might be too specific. We can report it to various levels of accuracy. To round to the nearest 10,000, we look at the 10,000s place, which is 2. Then we look at the digit to its right, which is 8. The rule is, if the next digit is 5 or more, we round up. Since 8 is greater than 5, we round the 2 up to 3, and all following digits become 0. So we get 30,000. To the nearest thousand, we look at the thousands digit, 8, and the next digit, 6. Since 6 is 5 or more, we round the 8 up to 9, giving us 29,000. To the nearest hundred, we look at the hundreds digit, 6, and the next digit, 1. Since 1 is less than 5, we round down, which means we keep the 6 as it is and change the following digits to 0. This gives us 28,600. But what if a number is exactly halfway? For example, let's round 16,500 to the nearest thousand. Here, 16,500 is exactly halfway between 16,000 and 17,000. The standard convention is to round up. So when a number is exactly halfway, we always round up to the next value. 16,500 becomes 17,000. Now let's practice rounding with a few examples. First, let's round to the nearest thousand. Consider the number 68,786. We want to round to the nearest thousand. The digit in the thousands place is 8. We look at the next digit, which is 7. Since 7 is greater than or equal to 5, we round the thousands digit up. So 8 becomes 9, and the number becomes 69,000. Next, let's try 74,245. The thousands digit is 4. The next digit is 2. Since 2 is less than 5, we round down. This means the 4 stays the same, and we get 74,000. Now, let's try rounding to the nearest hundred. For 6,858, the hundreds digit is 8. The next digit is 5. Because the next digit is 5, we round up. The 8 becomes a 9, giving us 6,900. Finally, let's round to the nearest 10. Let's take the number 485. The tens digit is 8, and the next digit is 5. Since the digit is 5, we round up. The 8 in the tens place becomes a 9, resulting in 490. Excellent. We've now reviewed how to round whole numbers. Next, we'll apply this to decimals. We can also approximate numbers by rounding to a certain number of decimal places, often abbreviated as DP. This refers to the number of digits we keep after the decimal point. The rule is the same. Look at the digit to the right of the one you're keeping. If it's 5 or more, round up. Let's look at an example. We want to write 7.864 to one decimal place. This means we want to keep only one digit after the decimal point. That digit is 8. To decide whether to round it, we look at the second digit after the decimal, which is 6. Since 6 is 5 or more, we round the first digit, 8, up to 9. So 7.864 rounded to one decimal place is 7.9. Let's try another one. Write 5.574 to two decimal places. Here, we want to keep two digits after the decimal. The second digit is 7. We look at the third digit, which is 4, to decide. Since 4 is less than 5, we do not round up. The second digit, 7, stays as it is, so 5.574 to two decimal places is 5.57. Let's do one more. How about 2.95 to one decimal place? We want to keep the 9. We look at the next digit, which is 5. Since it's 5, we round up. Rounding a 9 up means it becomes 10. So we write a 0 and carry the 1 over to the left of the decimal point. 2 plus 1 is 3. The answer is 3.0. It's important to write the, quote, 0.0 to show that we have rounded to one decimal place. So we've seen how to round to a specific number of decimal places. This is a crucial skill for presenting numerical results clearly. Another important method of approximation is using significant figures, or SF. Significant figures are the digits in a number that are considered reliable and contribute to its precision. This is different from decimal places. The first non-zero digit from the left is the first and most significant figure. For instance, in the number 43.25, the 4 is the most significant figure because it represents the largest value, 40. The 5 is the least significant, representing just 5/100ths. Let's see how to round to a specific number of significant figures. Suppose we need to write 43.25 to 3 significant figures. We identify the first 3 significant figures, 4, 3, and 2. To round, we look at the fourth significant figure, which is 5. Since the next digit is 5, we round up the third significant figure. The 2 becomes a 3. So 43.25 to 3 significant figures is 43.3. It gets a bit trickier with numbers less than 1. Let's write 0.0043 to 1 significant figure. In this number, the leading zeros are just placeholders. They are not significant. The first significant figure is the first non-zero digit, which is 4. We want to keep just this one. We look at the next digit, 3. Since 3 is less than 5, we don't round up. The 4 stays as it is. The answer is 0.004. Let's try one more. Round 48,599 to 1 significant figure. The first significant figure is 4. The digit next to it is 8. Since 8 is greater than 5, we round the 4 up to 5. We must keep the place value, so we fill the remaining spots with zeros. The answer is 50,000. Understanding significant figures is key to expressing measurements with the correct precision. Now let's talk about appropriate accuracy and estimation. When you use a calculator, it often gives an answer with many decimal places. In most cases, this level of precision isn't needed or helpful. We need to choose an appropriate degree of accuracy. A good rule of thumb, unless you're told otherwise, is to give answers to 1 or 2 decimal places, or 3 significant figures. For example, if we calculate 4.64 divided by 2.3, a calculator might show 2.0173913, and so on. Giving the answer to 1 decimal place is usually sufficient here. Rounding 2.017 to 1 decimal place gives us 2.0. Related to this is the powerful skill of estimation. Estimation allows us to find an approximate answer quickly, often in our heads. It's a great way to check if a calculated answer is reasonable. The key is to round the numbers in the calculation to something simple before you compute. Let's estimate the product of 57 and 246. We could round 57 up to 60 and 246 down to 200. 60 times 200 is 12,000. This gives us a rough idea of the answer. Alternatively, we could round 57 down to 50 and 246 up to 250. 50 times 250 is 12,500. Both estimates are close to the exact answer of 14,022. Let's try a division estimation. We want to estimate 6,386 divided by 27. Let's round 6,386 to 6,027 to 30. These are much easier to divide. 6,000 divided by 30 is 200. This is a good estimate for the actual answer, which is about 236.5. Estimation is a practical skill that helps build number sense and verify our calculations. We now move to a very important concept that arises from rounding: upper and lower bounds. When a number has been rounded, it represents a range of possible original values. The upper and lower bounds define this range. For example, the numbers 4.5, 4.50, and 4.500 look the same, but they imply different levels of accuracy. Let's focus on 4.5, which is rounded to 1 decimal place. What is the smallest number that would round up to 4.5? That would be 4.45. Any number smaller than this, like 4.44, would round down to 4.4, so 4.45 is the lower bound. Now, what is the largest number that would round to 4.5? This is a bit tricky. 4.54999 would round down to 4.5, but as soon as we hit 4.55, it would round up to 4.6. So the range includes everything up to but not including, 4.55. We call 4.55 the upper bound. We can show this on a number line. We use a solid circle at the lower bound, 4.45, to show it's included, and an open circle at the upper bound, 4.55, to show it's not included. As an inequality, if x is the original number, we write that x is greater than or equal to 4.45 and less than 4.55. The general rule is to find the degree of accuracy, halve it, and then add and subtract that amount from the rounded number to find the bounds. For example, if a height is 162 centimeters, measured to the nearest centimeter, the accuracy is 1 centimeter. Half of that is 0.5 centimeters. We subtract 0.5 to get the lower bound of 161.5, and add 0.5 to get the upper bound of 162.5. So the actual height, h, is between 161.5 and 162.5, including 161.5. Let's practice finding bounds. We'll start with a number expressed to the nearest whole number. Consider the number 83. It's rounded to the nearest whole number, so the accuracy is 1. We take half of the accuracy, which is 0.5. The lower bound is 83 minus 0.5, which is 82.5. The upper bound is 83 plus 0.5, which is 83.5. So the range of possible values for the original number x is 82.5 is less than or equal to x, which is less than 83.5. Now, let's try a number correct to 1 decimal place. Let's find the bounds for 3.8. The accuracy here is 1 decimal place, or 0.1. Half of this accuracy is 0.05. We subtract 0.05 from 3.8 to get the lower bound, 3.75. We add 0.05 to 3.8 to get the upper bound, 3.85. The inequality is 3.75 is less than or equal to x, which is less than 3.85. Finally, let's look at a number rounded to 2 significant figures. Consider the number 420, which is correct to 2 significant figures. This can be tricky. The significant figures are 4 and 2. The last significant digit, 2, is in the tens place. This means the number was rounded to the nearest 10, so the accuracy is 10. Half of the accuracy is 5. The lower bound is 420 minus 5, which is 415. The upper bound is 420 plus 5, which is 425. Therefore, the original number lies in the range from 415 up to, but not including, 425. Now that we can find the bounds of a single number, let's see how to calculate the bounds for calculations involving these numbers. When we add, subtract, multiply, or divide rounded numbers, the result also has a range of possible values, with its own upper and lower bounds. Let's start with a multiplication example. Suppose we need to find the bounds for the product of 34 and 65, where each is rounded to the nearest whole number. First, we find the bounds for each number. For 34, the range is 33.5 to 34.5. For 65, the range is 64.5 to 65.5. To find the minimum possible product, the lower bound, we must multiply the 2 smallest possible values together. That's the lower bound of 34 times the lower bound of 65, which gives us 2,160.75. To find the maximum possible product, the upper bound, we multiply the 2 largest possible values. That's the upper bound of 34 times the upper bound of 65, which is 2,259.75. So the true product lies between 2,160.75 and 2,259.75. Now let's look at division, which has a twist. Let's find the bounds for 33.5 divided by 22.0, where each is accurate to 1 decimal place. First, the bounds. For 33.5, the range is 33.45 to 33.55. For 22.0, the range is 21.95 to 22.05. Now, think carefully. To get the smallest possible answer from a division, we need to divide the smallest possible numerator by the largest possible denominator. So, we divide the lower bound of the numerator by the upper bound of the denominator. This gives approximately 1.52. Conversely, to get the largest possible answer, we must divide the largest possible numerator by the smallest possible denominator. That's the upper bound of the numerator divided by the lower bound of the denominator, which is about 1.53. These rules are crucial. For division, you mix the bounds to get the minimum and maximum results. Let's apply what we've learned about bounds to a practical problem involving geometry. We're asked to find the bounds for the area of a rectangle. The rectangle has a length of 10.0 centimeters and a width of 7.5 centimeters. Both measurements are correct to 1 decimal place. First, we need to find the bounds for the length and the width. For the length of 10.0, the accuracy is 0.1, so half of that is 0.05. The bounds for the length are 9.95 and 10.05. Similarly, for the width of 7.5, the bounds are 7.45 and 7.55. The area of a rectangle is length times width. This is a multiplication problem. To find the lower bound for the area, we multiply the two lower bounds together. 9.95 times 7.45 gives us 74.1275 square centimeters. To find the upper bound for the area, we multiply the two upper bounds together. 10.05 times 7.55 gives us 75.8775 square centimeters. So the actual area of the rectangle must lie somewhere between 74.1275 and 75.8775 square centimeters. This range reflects the uncertainty in our original measurements. This same logic can be applied to find the bounds for perimeter, volume, and other calculated quantities. Let's tackle one final problem that combines these ideas. We need to find the bounds for a length, given the area, and another length. We have a rectangle with an area of 400 square centimeters and a length of 20 centimeters. Both values are accurate to two significant figures. We need to find the bounds for the width. First, let's find the bounds for the given area and length. For the area, 400 to two significant figures means it was rounded to the nearest hundred. Half of 100 is 50. So the area is between 350 and 450. For the length, 20 to two significant figures means the 0 is significant. It was rounded to the nearest whole number. Half of 1 is 0.5. So the length is between 19.5 and 20.5. We know that width equals area divided by length. So this is a division problem. To find the bounds for the width, we'll use our rules for division with bounds. The lower bound for the width is the smallest possible area divided by the largest possible length. That's 350 divided by 20.5, which is approximately 17.07 centimeters. The upper bound for the width is the largest possible area divided by the smallest possible length. That's 450 divided by 19.5, which is approximately 23.08 centimeters. So, the width of the rectangle must be between 17.07 and 23.08 centimeters. Notice how much uncertainty there is in the width because of the way the area was rounded. Today, we have covered a great deal about accuracy and approximation. We started by learning how to round whole numbers and decimals, which is a fundamental skill for simplifying numbers. We then moved on to the concept of significant figures, a key method for expressing the precision of a measurement. We saw how to use these ideas to make estimations, a practical way to check our calculations and make quick judgments. Finally, we explored the important concept of upper and lower bounds, understanding that any rounded number represents a range of values. We learned how to calculate with these bounds, which is crucial for understanding the propagation of uncertainty in calculations. Mastering these skills will provide you with a solid foundation for more advanced topics in mathematics and the sciences. Thank you for your attention.